This is actually the chapter number 11 of our textbook, that is R.C. Hibbeler. Virtual work. So first of all, we can see that what do we mean by the term virtual work? So we have an idea that this virtual means something imaginary. And work, you know from the basic 11th class, what is work? That is whenever a force acts on a body and if it causes a displacement in the body, then we can say that there has been some work done. So see the block here in this figure, the initial position of the block is at A and some force is acting on this block at an angle of this alpha with the horizontal. If I extend its line of action, this is the force F. It is making an angle of alpha with the horizontal. Therefore, the force component which will be responsible for the displacement, you can see that this block has been displaced from point A to position A dash. Okay. So during this interval, this work done by this force will be equal to the force which is in the direction of the displacement. Okay, the force which is in the direction of the displacement, that is F cos alpha multiplied by this delta S, or we can say that this is equal to F dot delta S. Okay, so this is equal to F dot delta S because F dot delta S will be equal to F delta S cos alpha. Therefore, the work done by this force will be equal to F delta S cos alpha. Therefore, because this cos component is acting in the direction of the displacement. Or in other terms, we can see that along the line of action, this is the line of action of the force F. What is the displacement in this line of action, along the line of action of the force? You can see that this is the delta S is the displacement of the body. But what is the displacement of the body along the line of action of this force? You can see that this delta S, from this right angle triangle, we get that this distance is equal to delta S cos alpha. Okay, the component of delta S along the line of action of the force, we can see that it is delta S cos alpha. Therefore, again, we can see that this work done will be equal to the force and the displacement which has been produced along the line of action of the force, and that is equal to delta S cos alpha. This is the work done. And we can also see from these two relations that if alpha is 90 degree, then cos alpha will be 0. So we know that if the displacement and the force are perpendicular to each other, orthogonal to each other, then no work will be produced. Okay, there will be no work produced. What happened to this? Now again, we can see this figure, this third figure here. See, this is the force. Okay, this is the line of action of the force, and see what is the displacement. I can extend its line of action. This is the line of action of the force, and this delta S is the displacement. Okay, the block is moving from this initial position to the final position. And what is the angle between the force and the displacement here? It is equal to alpha. Okay, it's not theta, it is equal to alpha. Therefore, we can see that this du again will be equal to F delta S, and the angle between the force and the displacement here is this alpha, that is F delta S cos alpha. And now since this alpha is obtuse angle here, therefore this work done will be negative. And how can we say that? This F delta S, we can also write it as 180 minus cos alpha, isn't it? Sorry, 180 minus alpha. 180 minus theta. Okay, you can see that this theta plus alpha is equal to 180. Therefore, alpha will be 180 minus theta. Okay, and we know that cos of 180 minus theta, that is equal to minus theta, minus cos theta. Therefore, this will be F delta S cos theta. So in this case, the component of the force which is responsible for the work, you can see that we can break this into two components. One will be the vertical component and another will be the horizontal component. But this horizontal component of the force is acting in the direction opposite to that of displacement. Therefore, it is going to create negative work. The work done by this force will be negative. Okay. So these are the simple basic concepts which we have already learned in the 11th class. Now moving forward, now see here, there is a force acting on a particle. Okay, there is a particle at A force is acting on it, which creates a displacement from A to A dash. Okay, so here now we can say that the force might be variable. We can't always have the direction of the displacement. Okay, you can see that the motion of this particle from A1 to A2 is along some curve. Therefore, the displacement of this particle from A1 to A2 won't be having the same direction at all the points, because the displacement will be given by the tangent. Okay, we'll have this displacement vector here, it will be a tangent, and we will have another displacement vector at some different points. So at different points we will get different tangents. Okay, therefore what can we say here is that while the particle is moving from A to A dash, the work done will be equal to F dot dr. Okay, for a small displacement from A to A dash, that is, this displacement vector is equal to dr. Okay, so the work done during this small displacement will be equal to F dot dr. Okay, therefore the total work done in moving the particle from A1 to A2 will be the integral of F dot dr. Okay, so this is another relation which you can remember. Okay, although this won't be that much used, but this is from the basic classes which we have already learned. Now let's see what will be the work done by a moment. There is a rod. Let's say that the initial position is this black color position, that is, its initial position is 1. Let's apply some movement in the anti-clockwise direction. Let this moment be equal to m. So what is the work done by this moment when this rod reaches its final position, which is shown by the red color? We can see that if this is the total angle traversed is equal to theta, we can calculate the work done for a small displacement. This will be d theta. So work done by this moment during the small displacement from, suppose, position x dash to y dash, that will be equal to m d theta. Okay, so small work done while this rod is rotated by an angle of d theta from the initial position of x dash to the final position of y dash. Okay, in this small rotation, the work done will be equal to m d theta, and the total work done will be equal to integral of m d theta, that is, in moving the rod from the initial position 1 to the final position 2. This will be that is from position number 1 to 2. This will be the total work done. Okay. Also there it has the sign conventions that if m and d theta are in same direction, the work done is positive. Okay, if m and this theta are in the same direction, that is the displacement, the angular displacement is taking in the sense of the applied moment, then we can say that this work will be treated as positive. Now, and if they are in the opposite direction, then this work will be treated as negative. Okay, this will be treated as negative. So we can also see that sometimes a spring is connected. You might be wondering how this moment is acting in one direction and the displacement is in another direction. Let's take an example here. This is a rod. I'm again saying that the applied moment here is in the anti-clockwise direction. But the displacement is taking place in which direction? This is the sense of displacement. It is in the clockwise direction. So this work done, which is equal to md theta, this will be negative here. Okay, although the moment is acting in this anti-clockwise direction, but there might be some another element. Suppose there is a spring connected to this rod, which is exerting a spring force. There might be a spring force, suppose Fs, in this direction. Okay, although you are applying a moment in the anti-clockwise direction, but this spring force is creating a clockwise moment about this hinge. So definitely the moment produced by this spring would have overpowered the moment, applied moment, isn't it? Only then the body will move, only then this rod will move in which direction? In the clockwise sense. Okay, so no need to wonder that when can this moment at the theta be in the opposite direction. Okay, although the moment is in the clockwise direction, anti-clockwise direction, but the displacement here is in the clockwise direction. Therefore, here the work done by this moment will be negative. Work done by this moment will be negative. Fine. So these are some basic things which we are already aware from the school level. Now let's define something which is known as the virtual displacement. So something which is the virtual displacement. So till now, all the displacements, whether it is a linear displacement, that is delta S, or it is an angular displacement, that is d theta or delta theta. So all these were the real displacements caused by this, by these forces. Okay, these were the real displacements, isn't it? The block was applied some force, it moved by the distance of delta S. Okay, but sometimes there are certain displacements which we assume to exist. Okay, but they are not existing in reality. They don't exist in reality, but we suppose that some displacement acts in the body. Okay, so let's first of all define this virtual displacement. The imaginary or virtual moment of a body in static equilibrium. Which indicates a displacement or rotation that is assumed and does not actually exist. is called as virtual displacement. Okay, so these are the displacements which we assume to exist, but they are not acting actually. Okay, these are the virtual displacements. Let's take an example. Let's see an example here. Suppose there is a rod which is resting where, which is resting on a wall. One end of the rod is with the wall, and another end of this rod is where it is what we call as on the ground. There is a force. Suppose this force is equal to Q. This Q force is keeping the rod in the static equilibrium. So if we say that this is the center of gravity of the rod, then there will be what? A weight force. Okay, there will be a weight force acting on it, which will tend to move the rod in the downward direction. Okay, this weight has a tendency of creating a moment, and this rod can this end of the rod which is in contact with the ground can slip. Okay, so to keep this rod in the equilibrium, we have to apply some force which is equal to Q. Okay, we have to apply some force which is equal to Q, and I say that this system is in equilibrium at this position. Currently in this position, this rod is in equilibrium. Since this rod is in equilibrium, therefore there won't be any displacements. Let me take this end to be A and this end to be B. Since this rod is in equilibrium, therefore there won't be any displacement. Of the rigid body here. I am taking an example of a rigid body. Obviously, I'm stating myself that this rod is in equilibrium. This rod is in equilibrium. Therefore, there won't be any displacement in the body. Okay, there won't be any displacement in the rod. That is, the end A, which is in contact with the wall, will remain there. The end B, which is in contact with the ground, will remain in its place. But we have introduced a concept of virtual displacement. These virtual displacements are the imaginary or virtual movement of the body in static equilibrium. This body is in equilibrium, but still we say that there is some displacement. Okay, there is some displacement, but in reality, this displacement does not exist. We just imagine there will be some displacements in the body. Therefore, if I assume that there is some displacement in the body, although it won't exist, but I can still show that this here. See, this blue color is in the initial position. This is the initial position, and this is the final position of the rod. This was the end A, and this was the end B. This is the force here, isn't it? This is the force. So what has happened here? I have just shown some imaginary displacements, although this displacement won't be possible because the rod is in equilibrium. Therefore, it can't be in the motion. Under the equilibrium of this force system, this rod will be in its position, but still I'm showing some imaginary displacements. And I have shown the displacement of the point B. Therefore, this has to be its final position B dash, and this has to be the final position of A dash, of A, okay, that is A dash. Let me say that this has undergone some displacement, delta xb, since this is going in the x direction. Okay, this displacement is in the x direction. The displacement of point B is in the x direction. Let us denote this by delta xb. Also, the displacement of A, it is in the y direction. Therefore, I will assume that this displacement is equal to delta YA. Okay, although these are not the real displacements, this is not possible because the body is in equilibrium, but I'm imagining that there are certain displacements in the body. Now see here what will happen to the center of gravity. Initially, the center of gravity can be assumed to be here. This is G1. This is G1, okay? And after that, will the center of gravity in the final position lift or it will fall down? It will get raised by some amount, okay? Because the rod is going upwards, therefore, let's suppose that the final position of the center of gravity of the rod is G2. So again, here you can see that there is the displacement of the center of gravity. And I say that it has displaced by an amount. Since it is displacing in the y direction, therefore, the displacement of the center of gravity here is in the y direction. That is equal to how much? Y. We can say that it is equal to delta yg. Not only it has a displacement in the vertical direction, it has also a displacement in the horizontal direction. Let me assume that this displacement is equal to delta xg. Okay, so all these displacements are the imaginary displacements. Okay, so work done by these imaginary displacements. Let's see what is the work done by these imaginary displacements, and that work will be known as what? Imaginary work or the virtual work, isn't it? Okay, so let's concentrate on this point B. If we concentrate on this point B, we can take it. Let's see this point B. What are the forces that are acting on this point B? There's a Q force acting on this point B, and if I'm drawing the free body diagram of this point B, of this rod, in fact, there will be a reaction. This will be the reaction at the point B. Now, there is a displacement of the point B from B to B dash, and that displacement is equal to delta XB. Now say among these two forces, Q and RB, which force can be treated as responsible for the displacement? Obviously Q, because RB is perpendicular to the displacement, therefore it won't be able to do any work. So at B, we can say that this force Q creates an imaginary displacement. Therefore, the imaginary displacement multiplied by this force will give us what? Imaginary work. Okay, and that is the virtual work. So we can say that if at point B, we can say that the virtual work will be equal to what? This force Q multiplied by this displacement, that is equal to delta XB. So to differentiate the actual displacements from the virtual displacements, we use the term delta. The actual displacements will be represented by ds or dr, but this virtual displacements will be represented by delta x, delta r, delta y, or delta theta as well. Okay, when we are talking about the rotational displacements. Okay, so this is the virtual work done by the force Q at the point B. Will there be any virtual work at A? See, if I'm drawing the free body diagram here, there will be a reaction, isn't it? Now see, the displacement is from A to A dash. Will there be any work? There won't be any work because the force at A is perpendicular to the displacement. So no virtual work at A. No virtual work at A. We are seeing the virtual works where the forces are acting. Now see here, there was a force acting where, if I draw this free body diagram, I have to show the weight of the body as well. This is the weight of the body. It is acting at a centroid, center of gravity of the rod. Now, at G, what is the virtual displacement? There are two virtual displacements, one in the y direction and another in the x direction. But we will get virtual work from which displacement? In the y direction, because our weight is responsible for the virtual displacement. This weight and y, this delta yg, although they are in the opposite direction, but they aren't perpendicular to each other. Okay, while as delta xg is perpendicular to the weight. Therefore, at g, virtual work will be, this virtual work will be equal to minus w into this delta yg. This will be the virtual work where at when we are considering the weight force. Okay, the weight won't create any work when we are considering the horizontal displacement, because delta xg is perpendicular to w. Okay, so this is the concept of the virtual displacement and the virtual work. Although these displacements are not happening, therefore these works are not also in place actually. That's why we call them as imaginary work or virtual work, because in reality there isn't any kind of displacement, therefore there won't be any kind of work, hence they are termed as virtual work. Now, what is the principle of virtual work say? Principle of virtual work. Okay, this principle was given by Bernoulli. This was stated by Bernoulli, and it states that the principle of virtual work states that if a body is in equilibrium, then the algebraic sum of all the virtual work done by all the forces and couple moments acting on the body is zero. For any virtual displacement of the body. Okay, so this is the statement of the virtual work. It states that the summation of it and the algebraic summation of all these virtual works which are acting on the body due to what? Due to all these forces and the couples, their algebraic sum has to be zero if the body is in the static equilibrium. So if I apply this virtual work to the problem which I have just stated in the previous slide, the virtual work was done by two forces, that is the force Q and the weight. Therefore, this virtual work should be from the principle of the virtual work, du should be zero, which means that the work was due to, and in fact we are going to write delta u instead of this du. Delta u for the virtual work and du for the real works. Okay, so delta u has to be zero, and we had seen that this Q force is creating what? There will be a work due to this Q force, and that will be equal to Q into delta xp. And the virtual work was also by the weight, although it was opposite to that of the displacement, and the displacement was equal to delta. So from the principle of the virtual work, this has to be zero. Summation of the virtual work by all the forces and the couples acting on a body when it is in the static equilibrium, this has to be equal to zero. Okay, So this is the principle of virtual work. Now let's see this principle of virtual work for a particle. Although it's of no use for the particle, but still we can get some concept from this. There is a ball which can be treated as a particle. This is the ball, or any point mass which can be treated as a particle. Now there are various forces acting on this. Okay, you can see that it is surrounded by 4 springs. Therefore, there will be 4 spring forces, which has been shown on the FBD drawn below. Okay, so this system is in equilibrium. This system is in equilibrium. Therefore, it means that there won't be any kind of displacement in the ball since it is in equilibrium. Okay, it is in equilibrium, therefore there won't be any kind of displacement. See the free body diagram, assuming it to be massless. The ball is massless, therefore it hasn't considered the weight force in the free body diagram. So F1, F2, F3, F4, these are all the spring forces, and under the action of all these forces, this body is in equilibrium. Still, there has been assumed that there is some imaginary displacement of the body. See this ball here, which has been shown. Let me say that this is the final position of the ball. Okay, this is the initial position and this is the final position of the ball. This displacement does not exist because the body is in equilibrium. But still we have shown this is a displacement of delta R. The displacement vector here is equal to delta R. Okay. Although this displacement does not exist, but we have assumed that there is an imaginary displacement of delta R. So the virtual work will be equal to, in this case, the virtual work will be equal to delta U. Okay. Now the work will be due to how many forces? Due to all these 4 forces which will be responsible for creating the displacement delta R. So first force is equal to F1 dot delta R plus F2 dot delta R plus F3 dot delta R plus F4 dot delta R. So this is the summation of all these virtual works. Okay, and from the principle of work, from the principle of virtual work, their summation has to be equal to 0. Okay, this summation has to be equal to 0. So we can also write that delta U is equal to summation of the forces dot delta R vector. Okay, if I take this delta R to be common, I will get that F1 plus F2 plus F3 plus F4, that I write as the summation of all these forces. Okay, and these forces can be written in their components, that is summation of forces in the x direction, and we will have a I cap with it, plus summation of the forces in the y direction, we'll have a j cap with it, plus summation of the forces in the z direction, k cap. Okay, dot this displacement vector can be written in terms of their components. Okay, delta xi plus delta, this will be delta xi plus delta yj plus delta zk, and this dot product has to be 0 from the principle of virtual work. Therefore what we get here is that summation of the forces in the x direction, okay, computing the dot product, delta fx dot delta x, or simply multiplication, isn't it, plus summation of the forces in the y direction, delta y, plus summation of the forces in the z direction, delta z. This has to be equal to 0. So from here we get that. Now see here, we have assumed some imaginary displacement. Therefore we can't say that it is 0. We are ourselves assuming some imaginary displacement. Therefore this can't be 0. Okay. Delta y not equal to 0. Delta z is not equal to 0. When we are imagining some imaginary displacements, therefore we have to take them into some calculation. Therefore what will be 0 here is summation of the forces in the x direction, summation of the forces in the y direction, summation of the forces in the z direction. Okay, this is the equilibrium condition, which we have obtained from what? From the concept of the virtual work. Equilibrium equations for the particle. Okay, so although this virtual work will be no use for the particle, but still we have given a brief discussion regarding this. One more thing we can see here is that this is a ball, isn't it? This is a ball. Its center of gravity will be somewhere here. It is acted upon by two forces. One will be the weight of the ball and another will be the normal reaction exerted by the floor on this wall. Although this will be in equilibrium, but let us assume that there is some displacement on the account of the application of these two forces, a virtual displacement that is equal to delta y, isn't it? Okay, so if this is the initial position of the center of gravity, now let me say that this gets displaced, the center of gravity gets displaced to its final position, okay, and this g1 minus g2 will be equal to what? Delta y. Now if we see what are the virtual work, okay, if we see what is the virtual work done by the difference in the positions of the center of gravity will give us the virtual displacement. Okay, so this virtual displacement isn't existing actually, isn't it? There is no displacement at delta y, but still we assume that on the account of the application of these two forces, our center of gravity of this ball gets displaced by delta y. Now if we want to check, if we want to use the principle of work, this virtual work, now the virtual work will be due to two forces. One will be due to the weight and another will be due to the normal reaction. Okay, so virtual work due to normal reaction, it will be equal to how much? This will be equal to how much? Virtual work due to normal reaction. See, there is n force which is in the vertically upward direction, the displacement is in the downward direction. Okay, therefore the virtual work will be equal to minus n delta y. Now similarly we can see the virtual work done due to weight. The virtual work due to weight, this will be equal to what? Weight is in the downward direction, the displacement is in the downward direction, therefore this virtual work will be positive. Minus n delta y plus w delta y. So we also know from the principle of work, from the principle of virtual work, okay, that is delta u1 plus delta u2 should be equal to what? 0. Okay, but their algebraic sums have to be taken into account, therefore we will have minus delta y plus, this has to be 0. From here we can get that minus n plus w into delta y, this will be equal to 0. Now we have assumed some value of the virtual displacement, therefore we can't take it to be 0 because we are ourselves assuming some value of the virtual displacement. So from here we can get that delta y can't be 0 because we are assuming this some value of the delta y. So we will have minus n plus w, that has to be 0, which means that weight will be equal to the normal reaction. So this is simply from the equilibrium. Although this you might say that what is this method of virtual work, why is it hectic? But it will be quite useful when we are going to study this system of the rigid bodies. Okay, well, we are going to study the 2 or 3 rigid bodies in connection with each other. Okay, there it will be quite helpful. Okay, so these are just the basic concepts. So from the equilibrium equation we could have directly written that n is equal to w, and from the principle of work and energy from this principle of this virtual work, we also get the same concept. Okay. Let's take one more example. In the previous examples, we have discussed the virtual work principle for a particle. Now let us discuss the virtual work principle for a rigid body. So you can see that there is a simply supported beam having a roller support at A and a hinge support at B. So this beam is a rigid body and a point load is acting at the center of the beam, at the midpoint of the beam. So since we are having a roller support here, there will be a reaction in the vertical direction, that is AY, and here we have a hinge support, therefore there will be two reactions, one in the vertical direction and another in the horizontal direction, as has been shown here in the FPT. So actually this beam is in equilibrium. And we have also seen in the previous, while we are discussing the SFD and the BMD calculations, we have seen how to calculate the reactions. And directly we can say that since this is a simply supported beam and at the midpoint there is a load P, therefore the reactions AY should be equal to the BY, and this will be equal to P by 2, okay? That we know from the equations of the statics. So since this beam is in equilibrium, therefore there won't be any displacements. There won't be any displacements, okay? But what does virtual work principle say us? That give some imaginary displacement. Okay, and these displacements can be either in terms of the translation or in terms of the rotation. Now see here what kind of displacement has been given here. There is a displacement, that is the rotation of the beam has been given. Okay, this beam has been rotated about an hinge B by an angle of delta theta. Okay, since this is an imaginary displacement, therefore all the imaginary displacements will be represented by delta. So when this beam has been given a rotation about the hinge B by an angle of delta theta, we can see that this midpoint of the beam has moved some distance upwards. Okay, obviously it will move some distance upwards initially if we are going to have a beam here, and after the rotation by some angle, this point B will be here. You can see that the midpoint, let's treat this point to be C, it has moved upwards, and this point A is also moved upwards. Therefore if this was A here, this was C, so this will be C dash, and the angle, the rotation has been given by an angle of delta theta. Okay, since this is an virtual rotation, this rotation is not possible because this beam is in equilibrium. Okay, therefore this has been represented by delta theta, and there will be the displacement of these 2 points. This point will get displaced. Let us say that it gets displaced by delta y dash, as has been shown in this diagram, delta y dash. And let us say that the imaginary displacement of this point A is equal to delta y. Okay. Now we can see that what will be the virtual works. See here the external forces. One thing to note that internal forces are not considered in the virtual work principle. Why they aren't considered in the virtual work principle? Because the rigid body, first of all, does not deform on the application of the internal forces. And one more thing that can be seen here is that internal forces are equal and opposite.
That is, they act in pairs. Which means that the virtual works by these internal forces will get cancelled. Okay, so first of all, we have to see that we don't take into the account the internal forces while we are dealing with this virtual work principle. Next thing here is that we have to see what are the forces which are causing the imaginary displacements. Okay, so we can see that the forces have been applied at, we have the external forces ax, ay, okay, and the external force py. This is P, external force P, and this is external force AY, and there are external forces BX and BY. But one thing to note is that this point B is not getting displaced. Although there is a force Bx and there is a force By, but this point B hasn't got displaced. Therefore, the effect of these two forces won't be considered in the virtual work because these forces are not causing any displacement. For the work, the force should cause some displacement. Now see here in this case, this force Ay has caused a displacement of delta y. And you can see here at the midpoint, there is a displacement of delta y dash and there is a force acting which is P. Although the displacement and the force are in the opposite direction in this case, but still it has to be written in the equation of the virtual work. Okay. So applying principle of virtual work, we can see that the virtual work due to this force Ay, that will be equal to this, the force is Ay, and the displacement it is creating is delta y dash. Sorry, it is delta y. Okay. Therefore, this virtual work will be positive because the displacement is in the upward direction and the force is also acting in the upward direction. Okay. So this will be positive. Now we can see that this P is doing a virtual work. Okay. The virtual work due to this load will be equal to P is the load and the displacement at this point, okay, is equal to delta y dash. But since P and delta y dash are in opposite direction, the displacement is in upward direction while as the load is in the downward direction. Therefore, this virtual work has to be taken as negative. Now, from the principle of virtual work, we can say that the summation of all the virtual works due to all these forces and the external moments and couples will be equal to 0. And we have to take their algebraic sums, which means that Ay into delta y minus P into delta y dash. Now these displacements, delta y and delta y dash, these are the linear displacements. They can be represented in terms of this delta theta. Okay, so see here, this is a system of a 1 degree freedom system. Okay, that is, this delta theta is sufficient to explain the position or displacements of every point, isn't it? So we can bring this delta y in terms of delta theta and this delta y dash in terms of delta theta. Therefore, this one angle, that is the rotation of this beam, okay, the angle which it traverses, the angular displacement of this beam, delta theta, is sufficient to provide us the information regarding the displacements of all the points. Therefore, it is a single degree freedom system. Okay, number of degrees of freedom we define as the number of independent coordinates that will completely specify the position of all the points here. Okay, we can see that this delta theta is just enough to tell us about the displacements of all the points in the beam. Now we can see that this delta y will be equal to, from the geometry it is clear that delta y is equal to, this delta y is equal to L delta theta. Okay, for a small displacement of delta theta, this delta y will be equal to L delta theta. And this delta y dash will be equal to, for small displacement of delta theta, this will be equal to L by 2 delta theta. Okay, so we can substitute this relation here. We will get that ay into, in place of delta y, we can write L delta theta, and p multiplied by, in place of delta y dash, we can write L by 2 delta theta. Okay, so this has to be equal to 0. Now we can see that AYL minus PL by 2 delta theta has to be 0. Now we have assumed some value of delta theta, okay? Although there is delta theta, that is imaginary angular displacement. Does not exist, but we have assumed, therefore it will have some value, okay? Although it won't exist, but since in this analysis we are assuming some value of delta theta, we are giving an imaginary displacement, therefore delta theta can't be equal to 0. So from here we get that AYL should be equal to PL by 2. And we get that AY should be equal to P by 2. Okay, so AY should be equal to P by 2. This is the same reaction which we had obtained from the equilibrium equations. Let's discuss one problem on the principle of virtual work for a rigid body. You can see that there is a rod AB whose end A is in contact with the ground and end B is in contact with the wall. The weight, in fact, the mass of this rod is given as 50 kg, and the contacts are smooth, therefore we don't have to take into the account the friction forces. We can see that at the center of gravity of this rod, we will have a weight force. Okay, on the account of this weight, you can see that there is a tendency of the point A to move in this direction. Okay, that is towards right, and this rod, the contact point B will try to move in the vertically downward direction. Okay, so this is the tendency of the rod to move. Okay, it can slip at point A, and its point B will also come down. So to hold this rod in equilibrium, there has to be a force P applied. Okay, we need to apply some force P, and this is the force which we have to find out. Okay, we have to find out the magnitude of the force required to hold this 50 kg smooth rod in equilibrium at a particular angle, which is given as theta is equal to 60 degree. Okay, this angle is equal to 60 degree in this question. So let us discuss, let's generalize this question. We say that there's a rod of length L whose one end is in contact with the wall and another end is contact with the ground. We have to apply a load P in this direction, and the angle is equal to theta, so that this rod is in equilibrium. So if we draw the free body diagram of this rod, apart from this applied force, we will have a weight which is acting at the center of gravity. There will be a normal reaction that the wall is exerting to the contact point B. It can be represented by NB. We'll have a normal reaction at A. It will be represented by NA. Okay, so this is the complete free body diagram of this rod. Now let's give some virtual displacement, because in the principle of virtual work we have to give certain virtual displacement. Okay, so let us say that we are giving the virtual displacement in this direction, that is this point A is shifting towards left, and when this point A is shifting towards left, this point B will get raised. Okay, it will move upwards. So this is the virtual displacement which we are giving. Okay, these are the imaginary displacements. Okay, so in reality these displacements will not take place because this rod, this system is in equilibrium, therefore there won't be any displacements. But to apply the principle of work, this virtual work, we have to give some imaginary displacements, and the imaginary displacement here is that there will be a translation of the point A towards left, that is A will move from A to A dash, and B will get lifted from B to B dash. And during this thing, there will be also the rotation of the rod, which will be represented by delta theta. Okay. So we can see in this figure that the initial position is denoted by this blue color line, that is A point is here and B point is here. After giving some certain displacement, this point A moves to this position A dash and this moves to the position B dash. Okay. We can also see here that this angle was theta, and let us suppose that this displacement, this virtual displacement which we have given in the x direction is equal to delta xa. Okay, this is the displacement of the point A, therefore, and it is in the x direction, therefore we can write this to be delta xa. Now let's say that this point B has displaced by this much amount of distance and it is equal to delta. Now this displacement is taking place in the y direction, therefore let's say that this displacement is equal to delta yb. Okay, so we can also see that there will be certain rotation. Okay, there will be a certain rotation, that is which will be represented by delta theta. Okay, there will be a change in angle which will be represented by delta theta. So we can see that this is equal to delta theta. So we can represent these displacements in terms of delta theta. Okay, because again this is a single degree of freedom system. This delta theta should be able to give us all these displacements. Okay, that is, we will convert these linear displacements, this linear displacement delta xa and this linear displacement delta yb, into this angular displacement, that is delta theta. Therefore our aim is to represent this delta xa and delta yb in terms of this delta theta. Okay, so we can also see here that apart from this point A and point B, there has been a displacement of center of gravity as well. Okay, assuming that initial center of gravity was here, therefore I can write that this is G1, and let me assume that the center of gravity has shifted to this point, that is this is G2, and we can see that there will be a displacement both in the x direction and in the y direction of the center of gravity, but we are mostly interested in this vertical displacement. Why we are interested? Because the weight acting at the center of gravity is in the vertical downward direction. Therefore, the weight will only do the work when there will be a displacement in the y direction. Okay, we don't have to consider the displacement in the x direction of the center of gravity because the weight is perpendicular to the uh, x displacement, that is displacement in the x direction. Okay, so we are interested in the displacement of center of gravity in the y direction. So this means that this is the virtual displacement of the center of gravity in the y direction. See, remember that all these displacements are imaginary or virtual displacements. They don't exist in the real. But to apply the principle of virtual work, we have to consider these displacements. Now, how we are going to find these, what we call as these virtual displacements? This is the main thing which we have to see. Okay. So see here, there is a basic method to find it. First of all, we have to see what are all the active forces. We can also see here, if we are drawing the free body diagram, let's this point be A, we can see here there will be a reaction, normal reaction. This is the applied force P, as well as there will be a normal reaction at the contact of the rod with the wall. Let's suppose that this is equal to NB. And there was the weight force, which was acting in the vertically downward direction. Now this is the complete FBD, and what are the external forces? So remember that I had discussed that we have to see what are the external forces which are contributing towards the virtual work. Now see this, the forces. So in the FBD we have the external forces are this NB is an external force, that is the normal action at B. Normal action at A is an external force. This P is an external force, and this weight W is an external force. Okay, but out of these external forces, all want to be the active forces. Okay, what are these active forces which contribute to the virtual work? So the active forces are those forces which contribute to the virtual work. Now see this force NB, it's not an active force because the virtual work will be zero. See, this NB is acting where? At the point B, but the point B is displacing in the upward direction, while as this NB is acting in the horizontal direction. Therefore, NB and this displacement delta YB are perpendicular to each other. Therefore, this NB won't be contributing to the virtual work. Similarly, see this NA. NA is in the upward direction, while as the displacement of the point A is in the horizontal direction. Therefore, again, this displacement delta XA and NA are perpendicular to each other. Therefore, it's not an active force. That is, NA won't be contributing to the virtual work. But see here, this P is in the X direction, and the displacement is also in the X direction. Okay, whether positive or negative, but these are along some particular axes. Okay, that is, the force P is horizontal and the displacement delta XA is also horizontal. Therefore, this P will be contributing to the virtual work. Hence, we can say that the active forces here are this external force P is an active force, and this weight is also an active force because weight is acting in the downward direction, that is along the y-axis, and we also have this displacement in the y direction. Okay, although this weight is not contributing to the displacement in the x direction, but we will have a virtual work when we will multiply this weight with this virtual displacement delta yg. Therefore, this is again an active force. Okay, this is again an active force. What we do, we write the coordinates of the point of application of the active forces. So what we are going to do, we are going to write the coordinates of the point of application of the active forces. See here, this point is a point where an active force is acting. Okay, so it will have some coordinates. Let me denote those coordinates by xa comma ya. And here, this is an active force. There is an active force weight. Let me denote this coordinate by xg comma yg. Okay, so these are the coordinates of those points where the active forces are acting. Now there is no need to write the coordinates of this point B because there isn't any active force acting. Although there is a normal reaction, but it's not an active force. It's not contributing to the virtual work. Now see here, also I'm going to write this x, okay, this coordinate in terms of this theta, because we are going to express these displacements, okay, these virtual displacements in terms of the variable theta. Okay, so we can see that the xa coordinate will be equal to, from the geometry it is clear that the length of this rod is equal to L and this angle is theta. Therefore, xa is equal to xa will be equal to x cos theta. And similarly, we can see that I'm not interested in the y coordinate. Okay, for the point A, I will be interested in only the x coordinate because I have a differential displacement in the x direction only. So there is no need to write the coordinate of the y coordinate of A, because there won't be any displacement in the y direction of the point A. Similarly, if we am seeing the coordinate of G, see here the G is moving in the vertically in the upward direction. Okay, it is moving in the upward direction, although it is also having a displacement of this in the x direction, but the active forces are acting in the vertical direction. That is the component of the force which is responsible for the virtual work is only in the y direction. Therefore, I will only consider this displacement in the y direction. Therefore, for the point G, I will consider only this force, this coordinate in the y direction only, because my displacement will also be in the y direction, although the displacement is in the x direction as well as the y direction, but the virtual work will be considered only due to the weight, and that weight is acting along the y axis. Okay, that is in the y direction. Therefore, I need to consider only the y coordinate of the center of gravity. Okay, there is no need to write the x coordinate of the center of gravity. Okay, although there is no issue, we can write the x coordinate as well as the y coordinate. So the y coordinate of the center of, sorry, of the point A would have been 0. Okay, also now we can also write both the coordinates, there is no issue, but we can see that only the y coordinate of the center of gravity will be used. Okay, also if I write xg, okay, if I write this xg, we can see that this is g, it will have coordinate, that is x coordinate, and the y coordinate. This distance will be equal to L by 2, and this distance is also equal to L by 2. So we can see that this distance will be equal to L by 2 cos theta. Okay, this is cos theta. This distance, that is the x coordinate, will be equal to L by 2 cos theta. And the y coordinate of the center of gravity, that will be equal to L by 2 sine theta. Okay, I can take this right angle triangle here. Okay, this lower triangle, we can see that this height, okay, height of the center of gravity from this x-axis will be equal to L by 2 sine theta. Now, from the principle of virtual work, we can see that there will be virtual work due to Q. And this virtual work due to this force, in fact, P, it is here. The virtual work due to this force P will be equal to the force, that is P, and the virtual displacement, that is equal to delta XA. Okay, P is acting at A, therefore it is creating a virtual displacement delta XA. Also, virtual work due to weight, that will be equal to, now see, this weight is in the vertically downward direction, while as the center of gravity is moving upwards by a displacement, that is the imaginary displacement of delta YG. Therefore, this virtual work will be negative because the weight and the displacement are in the opposite direction. So, from the principle of the virtual work, we get that delta U, in fact, because these are the virtual works, delta U, that is equal to the P delta XA minus W delta YG. So this has to be 0. Okay, now we have to find these differential displacements. Okay, we have to find these differential displacements in terms of delta theta we will find. So we know that in fact we know that XA, that is the x coordinate, of A is equal to, this is equal to L cos theta. And this y coordinate of the center of gravity is equal to L by 2 sine theta. Okay, so differentiating both of these, that is, to calculate this differential displacement, we have to differentiate it, that is delta xa. Okay, in place of dxa, we will write delta xa because these are the imaginary displacements. Okay, to differentiate them from the real displacements, we write delta xa. So this will be equal to minus L sine theta. The differentiation of cos theta is equal to minus sine theta. Therefore, L sine theta delta theta. Similarly, performing the differentiation of this, we will get that delta yg is equal to L by 2 cos theta delta theta. Okay, so now we will substitute these values here in this equation. Okay, we'll substitute the value of delta xa and delta yg in the above equation. So one thing is that the sign conventions, since I have taken the since I have taken in this, while I'm substituting this delta xa here, I will substitute only the magnitude. Okay, we'll substitute the magnitude only because I have been consistent with the direction of the displacement and the load. The displacement and the load, this displacement delta xa and the load p were in the same direction. Therefore, I have already considered the sign convention. Therefore, I will substitute only this magnitude in this equation. Therefore, what I will get here is that delta u will be equal to p into L sine theta delta theta minus w into this virtual displacement of the center of gravity in the y direction, that is equal to L by 2 cos theta delta theta. So this has to be 0. Okay, so we can simplify this equation. This delta u, that is equal to, we can take out L delta theta to be common, or we can take delta theta to be common, and in the brackets we can keep PL sine theta minus WL by 2 cos theta. So as per the principle of virtual work, this has to be equal to 0. Now we have assumed some imaginary displacement of delta theta. Delta theta can't be equal to 0, although it is 0 in actual, but we have assumed it to have some certain value because we are giving certain imaginary displacement. Therefore, this term can't be 0. Therefore, what will be 0 here is that PL sine theta minus WL by 2 cos theta, this has to be 0. So from here we will get that L and L will cancel out. P sine theta will be equal to W by 2 cos theta, which gives us that P is equal to W by 2 cos theta by sine theta, which gives us that P is equal to cot theta. Okay, so this is the equation of the force. Okay, so this is the equation. This gives us the magnitude of the force required to keep this rod in equilibrium. Okay, one more thing is that what I have used here is that we have already decided about the sign conventions. Since P and delta xa were in the same direction, therefore I have assumed them the work to be positive. Okay, since P and delta xa were in the same direction, I have assumed the work to be positive. Whereas the work, okay, the virtual work will be negative due to this weight because the weight was in downward direction and the displacement delta yg was in the upward direction. Okay. One more thing is that what could have I assumed that I would have simply wrote that this is an alternate method. I could have made a summation of the virtual works to be 0, and I would have wrote that I could have written that the delta u is equal to 0. That is the summation of all these virtual works have to be 0. What I can write here is that this load P is acting in the negative x direction. Okay, you can see that this is in the negative x direction. I have treated this to be positive. Okay, so first of all, I had selected this to be the origin. Okay, this point was to be origin. These all the coordinates had to be written from a particular reference axis. I treat this point to be the origin of the reference axis. Okay, this is the origin of the reference axis. So this was here in the y axis and this is the reference x-axis. We can see that this is the reference x-axis, that is x is positive towards the right direction and it will be negative towards the left direction. So in this case, we can see that this P was acting in the negative direction. Then I could have used a sign convention that P is in the next negative direction. This P is in the negative direction, therefore this will be written as minus. And delta xy, sorry, delta xa, okay, what is the delta xa that I had got? I had got that delta xa is equal to minus L sine theta del theta. So here in this case, I have to include this negative sign. Minus L sine theta I have to introduce a negative sign here. Okay, so this will be the virtual work due to this force P. Okay, so the difference is here is that here in this equation, well, when I was writing this equation I had already taken the care of the algebraic sum of the forces. Okay, so sorry, the algebraic sum of the work. Okay, I had seen that P delta xa is positive work because the P and delta xa are in the same direction. Okay, therefore, while I am taking this care of the works, the sign of the algebraic signs of these virtual works, all okay, in the first instance, then I don't have to include these negative signs, okay, that are occurring in these virtual displacements. But if I'm not taking the algebraic signs of the works in the first instance, okay, so here I write that this load P is acting in the negative x direction, then I have to include this negative sign as well. Okay, you can see that again this minus and minus will again be equal to PL sine theta delta theta. Now plus, see here I am writing plus, that is I'm not taking into the account the algebraic sign of the work. Okay, now this virtual work due to the weight will be due to the weight in the downward direction. The weight is acting in the downward direction, that is in the downward direction this weight is to be taken as negative because it is acting towards the negative y-axis. Okay, and here the displacement in the y direction, that has to be taken L by 2 cos theta delta theta. Okay, L by 2 cos theta delta theta. So this has to be 0. Again I will get that PL sine theta into delta theta minus W L W by 2 L cos theta delta theta. This has to be 0. Again delta theta can't be equal to 0, so from here we get that P will be equal to W by 2 cot theta. So there are two ways by which we can take the sign conventions. Okay, either you at the first instance decide that you take the algebraic sums, okay, of the virtual work. Since in the first instance I had taken the P and displacement to be in the same direction, and I had taken that work to be positive, therefore there was no need to include the negative sign here. See, in this case, I didn't include this negative sign of L sine theta, delta theta. I only included the magnitude because the care of the sign has been already taken, because I had taken this to be the positive work. Okay, P delta XA both were in the same direction, therefore it was positive. Whereas in this case, W and delta YG were in the opposite direction, therefore I had introduced the minus sign at the first instance. But see here, in this alternative method, I didn't include the signs of the work. Okay, I took that minus P is that this P load is acting in the negative X direction, therefore it has to be shown with the minus sign, and then I will give the differential displacement with its sign, okay, that had been obtained by the differentiation of this coordinate. Okay, so once you got this result, then as per our question, the value of P would have been equal to, the mass was 50, this is equal to 9.81, this was 2, and we had to find the value at cot 60 degree. Okay, in our question, the mass was given as 50, and this what we call as the angle was given as 60, where we had to say that what is the force required to keep this rod in equilibrium at theta is equal to 60. So you will get the value of P from here.